Hello folks, welcome back to Physics with Captain Rod. So I'm making this video to talk about number 65 in your Hibbler text here. So again, you know what we're looking at here, we have this acceleration function, this nice linear acceleration function which was given in the problem. I'm going to go ahead and write it 75 minus cx, where the c is equal to 0.025. The x is the x coordinate measured from maybe this position. I'm getting this right from the initial conditions of the problem, that at x equals 0 or at t equals 0 the plane is at rest. So I'm going to go ahead and measure it from its starting point. The first part of this problem is relatively straightforward. All right, so acceleration can be written a couple different ways. dv dt, one of the most common, but it can also be written by the chain rule differentiation, dv dx dx dt. So for the first part of the problem, I'm going to focus on writing the acceleration equals dv dx dx dt. Now keep in mind that dx dt is v. So that allows us to write this equation right here. We'll do this side first. V dv dx, right, has to equal the acceleration, which is given by this function, 75 minus cx. And this is a really easy separable type of function here. So we're going to have v dv equals 75 minus cx dx. And then this is solved by integration. Now, you can either choose to put limits on it or use indefinite integrals. I'm just going to use indefinite integrals here. So the left-hand side is going to integrate to v squared over 2 equals. Right-hand side is going to integrate to 75x minus cx squared over 2 plus a constant. And it's reasonably easy to show that. All right, now, taking note that when x is 0, the velocity is 0. So when you put a 0 here, here, and here, and you inspect that constant, you solve for that constant, you get 0. So our equation between speed and position is given by the v squared over 2 equals 75 minus cx squared. So I'm going to go ahead and kind of store this over here. So we got v squared over 2 equals 75x minus cx squared over 2. Keep in mind the c is 0.025. So the first part of the question says something like, you know, what is the speed when the planes travel 1,000 feet? I'm not even going to bother doing that. You folks can do that. So, you know, you put 1,000 here, here, solve for v. It's no problem at all. All right. Now, as I remember from class, you know, the second part of this problem, you know, we weren't quite sure how to get it worked out. But like usual, you know, it just takes a little bit of thinking and trying some different things. So let me get rid of this here and I'll talk about that second part. All right. The second part of the question, if I remember right, was what is the speed? Oh, I'm sorry, no. How long did it take to get basically to this point on the graph? Where, you know, so what is the time when x is 1,000 feet? So time information now. So, you know, when I kind of look at this, you know, we already did this. If we try the other one, we're going to have 75 minus cx equals dv dt. But there's three variables there, v, t, and x. So after staring at that for a while, I decided to come back and focus on this again. And I know I warned about not doing that in class because the you know, resulting equations would be pretty complex. And I was right. It was pretty complex, but I did manage to get it solved. So I'm going to talk a little bit about how. So we're going to come back here. I'm going to write that equation, dx dt squared equals, now the dx dt is coming from the v. So that's v squared. And I'm going to go ahead and put this 2 over on the right. This is now going to read 150x minus cx squared, because, you know, this 2 will cancel that 2. And this is an equation relating x and t, and that's what we need. I mean, that's what we were asked for. Find t when x is 1,000. So I decided to push this through a little bit and see where I could get with it. Square rooting both sides, this is going to read dx dt is going to equal the square root of 150x minus cx squared. This thing is in fact separable. We can rewrite it. Oh, get out of there. I don't want that there. We can write it dx over square root 150x minus cx squared equals dt. Really, pretty simple. What's not simple is the integral, or different integration of that function. So let me talk about how I decided to do that. Let me get this written up high here. Right? So the solution of that equation comes from integration of both sides. So what we have to do is we have to solve the equation. Integral dx over square root 150 minus cx squared is going to equal integral dt. Now I'm going to go ahead and talk about limits. T is starting at 0, going to some unknown time we don't know. The limits on x are numerical for this question. We're talking about over to 1,000 feet here. So the limits on x, 0 to 1,000 feet. What we don't know is the t that goes with that 1,000. So this actually, depending on how you try to work it, isn't too bad. Give me just a moment here, clean this up. I chose to do this thing numerically. As I study this integral, and I think about the different ways to integrate it. All right, method number one, for the people that like to give up easy, you could go to the textbook and see how they integrate it. Or method number two, go to integral tables. As most of you know me, I don't like to do that. I like methods that are robust and always work. And I think back, what type of methods do we focus on that always work? And the answer to that's numerical. This has been reduced to a numerical problem. If we study this integral here, right, the right-hand side is no problem. It's t. T is equal to the numerical value of this integral. So what I'm going to do is I'm going to reduce this to an area problem. Right? This is basically in the form integral f of x dx from 0 to some limit, b, where the product of the two, f of x dx, is an area. So what we have to do is find the area bound under this curve, where the function is the square root 1 over 150, actually I think it's 150x minus cx squared. I think I just caught that. I think I lost that x, yeah, right there. My apologies. That's an x. If you were wondering that in the video, yep, there it is. I got it. Now, before we even get to that, the function we're looking at is 1 over 150x minus 0.025x squared. A thing to notice is that this function's not defined at x equals 0. Looks like it's got asymptotic behavior. But if you think back again from calculus, just because a function has a vertical asymptote, that doesn't mean you can't integrate right up to that asymptote and find an area. So I'm going to go ahead and try to push this through numerically. And the idea here, I'll just chat about it, and I'm going to make a completely separate video on the numerical solution. But the idea is basically this. Given this function, and again, the function is 1 over square root 150x minus cx squared. This function presumably maybe looks something like this. I don't know what it looks like exactly. Out to x equals 1,000 feet. I'm going to calculate or define a delta x, and that's going to equal 1,000 over some number of rectangles that I'm going to choose. Now, when I work the integral out numerically, I started with 10. But one of the things you have to work on numerically is, you got to see if your answer's converging. I increased it to 20 and the number changed a little bit. So I increased it to 50 and the number changed a little bit. And I increased it to 100. And the number I got out this was, I think I ended up with 5.2 something seconds. And again, I'm going to make a completely separate video on how I did that. The numerical answers seem to be converging to about 5.2. I think I looked this up and it was like 5.3 or 5.28 or something like that. So I was close enough that I knew I was on track. If I needed more accuracy, we just increased this number larger and larger and larger. But the idea, again, is to define a delta x, figure out a way to get a bunch of x values as a function of some dummy variable I, where in this case I is going to run from 1 to, I think I left it off at, I got to check my computer here and look. I ran it out to 100. So I went ahead and I had to get to 100 points to get this darn thing to converge. We're going to find a formula for x, and again, what I'm going to do here is make a video detailing this, but basically it's equal to 0 plus I times delta x minus 0.5 times delta x. For those of you who see me do numerical work in class, I call this the Goldilocks Method. So I ran my x values from 0 to 1,000. I actually ended up just short of 1,000, 990 something. Then we're going to take our function value, multiply it by our delta x to find an area. So basically we're kind of doing this type of thing. And then I added up all the areas. Out came 5.2 seconds. So this was just meant to be kind of an overview of how we do it. I'm going to work this in much more detail and actually show how I went through the numerical calculation in a separate video. So, I mean, we were right on track in class. We had this far. I mentioned in class this is going to yield a very difficult equation to solve, and I was correct. I mean, looking at this, that's a pretty tough integral. I'm not quite sure how to do it analytically. My advice with integrals is always this. If it looks like Pythagorean theorem, trig subs might work. So my guess is that we might try this with some sort of trig sub. But again, the numerical method worked great. Kicked out 5.2 for an answer, and I consider it done. So I'm going to call that done right now. Make another video on how to actually do the math solving that equation. So everybody have a great day.